let's go ahead and briefly, just so everyone can really kind of believe it, talk about why the derivative of e to the x is actually the x. I know last class we graphed e to the x. I talked about how, like, oh yeah, if you look at the function e to the x, the slope of the tangent line, in fact, let me draw it again so everyone can see it again. So if you graph e to the x, you have to actually graph it pretty accurately to make this picture kind of work. So I know that e to the 0 is 1. I know that e to the 1 is e, which is about 2.7. E to the negative 1 is about 0.36. So that's some good points to have. So what I'm trying to point out here is that at the point 0, 1, the slope of the tangent line is 1. And at the point 1 comma e, the slope of the tangent line is in fact e. And that's true for any point on the graph of e to the x, that the y value of your coordinate is the same as the slope of the tangent line at that point, which is super cool. We can also use the limit definition of the derivative to see that this is also true. So if you look at, so here's our limit definition, right? The derivative of e to the x is the limit as h goes to 0 of, right, this here is our f of x plus h minus f of x all over h. So I've just got e to the x plus h minus e to the x all over h. And then I'm just doing a little bit of simplifying. So e to the x plus h, I'm going to rewrite as e to the x times e to the h. So then I've got the limit as h goes to 0 of e to the x times e to the h minus e to the x all over h. And then from here to here, I factor out e to the x from the top. So now the top is e to the x times the quantity e to the h minus 1. Still the same expression, right? It's the limit as h goes to 0 of e to the x times e to the h minus 1 over h. And then we do something. We say, well, look, x doesn't care what h is doing, right? H can go to 0 or a million. E to the x is still e to the x. So anything that doesn't have the variable that's changing in your limit, anything that doesn't have that variable can actually move out in front, right? The limit doesn't affect it at all. It's kind of like how you can pull a constant out in front of a limit. Same thing with a variable that's not kind of having to do with the variable that we're taking the limit of. Do the same sort of thing. So then we can do this e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And here's where we do something super sneaky. Say, well, look, I know, and we've talked about this before, the limit as, we used x before, I'm using h now. The limit as h goes to 0 of 1 plus h to the 1 over h is equal to e. Before, like in class the other day, he definitely said, the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. Same thing, just a different variable. But now here's what I'm doing. I'm saying, well, I'm going to replace e, specifically that e right there, with this limit. So I rewrote e as 1 plus h to the 1 over h, and then it's still raised to the h power. And then the limit is already there. It's kind of a little tricky, right? It's like, well, I'm not writing the limit exactly, but it's over there. It's still the same thing though, right? The limit of this part here is still e. But then things simplify super nicely. The 1 over h and h powers cancel out. So you just get e to the x times the limit as h goes to 0 of 1 plus h minus 1 over h. The 1's cancel, and then h over h is 1. So you e to the x times 1 to e to the x. Kind of cool. So there is more justification that the derivative of e to the x is in fact e to the x. All right. Are there any questions about this particular example? Again, you don't have to know how to reproduce this, but it's good to have seen it so you can really kind of deep down believe that the derivative of e to the x is in fact e to the x. Although, to be perfectly honest, I think that keeping this picture in your head of the function e to the x and being like, oh yeah, I know at the point 0, 1, the slope of the tangent line is 1. and I know at the point 1 comma e, the slope of the tangent line is in fact e. I think that might be a better way to remember, oh yeah, the derivative of e to the x is itself e to the x. All right. Sorry, I didn't give you much of a chance to ask questions, so I will erase silently for a moment, and you can think of a question if you have one. I'll also take a picture of there. It's funny, in the 17D class I was co-classing for last quarter, I was watching the lectures that the teacher was doing, and she would have students do like this, what you have to do, like you had like a pre-lecture reading or videos to watch or some stuff, and you also have to like submit, like say things you didn't understand. And so then in the lecture, she would go over something and then be like, okay, does anyone have any questions? And she would wait. She'd be like, I know somebody has to have a question because you guys said you didn't understand this in the pre-lecture, whatever. And so she was really like, I'm just gonna wait until someone asks a question. I'm not gonna do that. But if you have questions, definitely ask them. So let's talk about how to differentiate functions that have e as a base. Something like, I don't know, f of x equal to e to the x squared plus 3. So here's the idea. Every derivative you know how to do, there's kind of the basic version of it and the chain rule version of it. For example, if my function was, I don't know, say something super straightforward like tangent of x, we know the derivative of tangent of x is secant squared of x. And in a similar way, we know that if we use the chain rule, say if our function is, let's actually make it very similar to what we've got going on here. Let's say our function was tangent of x squared plus 3. The derivative of that would be, well, here's how I usually say it. I usually think of this as I have a function that is tangent of some stuff. And the derivative of tangent of some stuff is, well, I know the derivative of tangent of x is secant squared of x. So the derivative of tangent of some stuff is secant squared of your stuff times the derivative of the stuff. So this is my stuff, or people often call it u. I usually call it stuff. The derivative of tangent of some stuff is secant squared of your stuff times the derivative of your stuff. Right? That's the chain rule. You take the derivative of the outer function. The outer function here is tangent. Its derivative is secant squared. But the insides, the u or the g of x, as some people call it, stay the same. And then we multiply by the derivative of the inside. That's our chain rule. And it works literally for any function you know how to take the derivative of. So for example, we know the derivative of e to the x is e to the x. So the derivative of e to the stuff, well, the derivative of e to the x is e to the x. So the derivative of e to the replace x with stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Same idea. You're just taking the derivative and multiplying by the derivative of the inner function, which usually is in the exponent. So let's do some more examples. Let's say, let me actually, I know I had some, where are you hiding from me? Sorry, one moment. I had lots of great examples and they all disappeared. Oh, fine, okay, fine. So let's say our function was e to the x cubed plus 7x minus sine of x. Right, quite the exponent there. Derivative is still very straightforward. Here's something nice about exponential functions like e to the something or 2 to the something or 3 to the something. If you're ever differentiating an exponential function, its derivative will always have an exact copy of itself. So the derivative of e to the something is e to the something. So I get e to the x cubed plus 7x minus sine of x times, we have to multiply by the derivative of the stuff. So the derivative of my stuff is, let's see, 3x squared plus 7 minus cosine of x. Or we can ask to say take the derivative of, this will be fun. Let's say it's going to be e to the x to the 4th times secant of x. So now our derivative is going to be, well, let's see, it's still e to the something, or e to the stuff. The derivative of e to the stuff is, in fact, I'm just going to write it like this. It's going to be e to the stuff times the derivative of the stuff. So that's going to be e to the x to the 4th times secant of x. And then the derivative of x to the 4th times secant, we have to use the product rule. So it's going to be the derivative of x to the 4th, which is 4x cubed, times secant of x, plus, then we flip it, right? We leave the x to the 4th alone, and we multiply by the derivative of secant of x, which is secant of x times tangent of x. Okay. So here's what we've got so far. And these are definitely, yeah, I don't love having to memorize stuff, but some stuff you just have to memorize. So these are definitely rules you want to memorize. You definitely want to memorize that the derivative of e to the x is e to the x. Really, it's like the easiest one to memorize because it's just itself if you are different. And then the derivative of, people write this a couple different ways. You can say the derivative of e to the u is e to the u times du dx. This is not my favorite notation. I prefer to write it as the derivative of e to the u of x, right? Make it a little more obvious that that exponent is actually a function of x. And then that's going to be e to the u of x times u prime of x. Right? Same stuff, right? Literally, e to the u and e to the u of x mean the same thing. I just didn't write in this line that u was a function of x. It still is a function of x. I just didn't make it very explicit. But honestly, my favorite way to write it is that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's what I say in my head every time. Right? When I'm literally like the words I'm saying out loud when I'm taking the derivative of either something or either stuff are the words that are going on in my head. So I really, really, really recommend when you have a function that's more complicated, like you see you're going to have to use the chain rule because you have some stuff that's not just x, say the word stuff. It helps. Okay. Let's do a couple more. So of course, you know, all of our other, oh, can you write the derivative of e to the xy? So yes, we'll get there. So let me ask you a question, Heidi. Do you mean I've got, you mean like that, right? Okay. I feel like there needs to be more to the problem than just that. We probably need to have an equation. Like maybe you have something like e to the xy equals x squared plus y, or something like that. Does that seem like what's happening? Okay, cool. So yes, this is exactly getting at the heart of implicit differentiation, which is going to be super important for the next few types of derivatives we actually take. So this is an excellent question. So I should kind of back up for a step. When you see something like this, when you have x's and y's mixed together, jumbled up, and they're asking you to find y prime or dy dx, or the derivative of y as a function of x, we have to recognize that we are assuming y is a function of x. I'm going to write this in a slightly different way just to kind of make it super duper explicit. And then we will, and then we'll do it both ways. And I'm actually going to change this a little bit just to kind of point out one extra thing. I'm going to make this x squared plus y cubed. just for fun. I'm going to rewrite this as e to the x times f of x equal to x squared plus f of x cubed. Just to make it super duper, like no bones about it, we know that y is a function of x. So now we're going to differentiate both sides. Differentiating e to the x times f of x, well, again, I'm going to take the derivative of e to the stuff. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of this is going to be e to the x times f of x. I'm probably going to run out of room. I'm going to erase these rules over here. No, I'm fine. I'm going to use it. E to the x times f of x times the derivative of that stuff. Okay, the derivative of x times f of x is a product. You have to use the product rule. Sort of x times f of x is going to be the derivative of x, which is 1. Leave f of x alone. Plus x times the derivative of f of x, which is f prime of x. Equal to, okay, I think I can make this fit. The derivative of x squared is 2x. And the derivative of f of x cubed, well, the derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. So here's what I would encourage you to do. If you see that you have x's and y's mixed together, and you know you're going to be using implicit, just think to yourself, okay, y is a function of x. Y is some stuff. And whenever we say the word stuff, we're always having to multiply by the derivative of that stuff. So if I was actually looking at it this way, the way I would take the derivative of both sides would be, okay, the derivative of e to the stuff here, I know it's okay. I'm using stuff in kind of different ways. Not really different ways, just in the bigger and the smaller sense. So the derivative of e to the something is e to the something times the derivative of something. The derivative of x times y is, well, the derivative of x is 1 times leave y alone plus x times the derivative of y is the derivative of y. Or you can say the derivative of y is 1 times the derivative of y, which is right? But it seems silly, right? If you're taking the derivative of just y, you're getting literally just the derivative of y. On the right-hand side, derivative of x squared is still 2x. And the derivative of y cubed, well, the derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. So that's the process for doing one like this. And then, of course, we have to do the algebra to solve for y prime. That's where you have to do some distributing, some isolating. Let's see. So on the left-hand side, I'm going to distribute this to each of those terms. So I'm going to get y times e to the x. I usually write this stuff out in front of the exponential. So you get y times e to the xy plus xy prime times e to the xy equal to, I'm going to run out of room here, 2x plus 3y squared y prime. And then we're going to group all the things about y prime on the same side. I don't care which side. Usually I'm trying to pick the side where it's easier. In this case, it's the same amount of movement either way. So you can either move this to the right and this to the left, or vice versa. This to the left and this to the right. Let's do this that way. So I'm going to bring all the y prime things to the left side. So I'm going to have x y prime times e to the xy minus 3y squared y prime equal to 2x minus y e to the xy. Factor out the y prime. So I'm left with x e to the xy minus 3y squared equal to, same thing over here, 2x minus y e to the xy. And then finally, we divide by all of this. So y prime is going to equal 2x minus y e to the xy divided by x e to the xy minus 3y squared. There's almost never any canceling you can do. Occasionally, you can factor out like a 2 on the top and 2 on the bottom and cancel that. But really, there's almost like never any simplifying that happens here. Definitely not here, right? You can't cancel these e to the xy, so you have to be able to factor the thing out to be able to cancel it. Good question. I like this one. It's very, yeah. So, yeah, we'll do some more like this. as we go along here. But I want to do, yeah, let's see what I want to do. Let's do a couple more examples of taking derivatives just exponentials, and we'll kind of roll back around to maybe a few more implicit examples. I got some implicit ones. I can throw at you guys. But I want to do at least one quotient rule one. Yeah. Let's say our function was, what have I got here? Sure. Let's say it's something nice and complicated, like e to the 4x over, yeah, let's make it gross, x plus cotangent of x cubed. Nice. Not nice. Okay. Typically, something to be aware of. Most of the time when someone gives you something like this to differentiate, you do not need to simplify it. Usually they will say, like, I've given questions like this on test, like, do not simplify your answers. If someone says that, take their word for it, right? You don't want to spend any time simplifying it. You want to spend your time efficiently on your exam. So don't simplify unless you have to. Sometimes you do have to because we're trying to like find a critical value or something, set the derivative equal to 0, and you can simplify it then, but not in this case. Let's find the derivative. Also, your questions are very much welcome. Thank you, Heidi, for the question. Good question. Happy to entertain other questions if you guys have them. Let's see here. So, I'm going to use the quotient rule. It's going to be the bottom, so x plus cotangent x cubed, times the derivative of the top. Okay, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. Minus, then we flip it, or reverse it, or vice, I usually say vice versa, right? Bottom times derivative of the top minus the top times the derivative of the bottom. Again, for the derivative of the bottom, we're going to have to use the chain rule, right? I've got some stuff cubed. The derivative of some stuff cubed is 3 times your stuff squared times the derivative of that stuff. The derivative of x plus cotangent x is 1, and the derivative of cotangent is negative cosecant squared x. So it's 1 minus cosecant squared x. I'm going to leave that a little bit wrong for just a second. And then over the denominator square, which will be x plus cotangent x to the 6th, right? Because you square a cube, it's going to be a 6th power. All right, now I've made a tiny, tiny error. It is important though. When you have these quotient rule things, and it's the bottom times the derivative of the top minus the top times the derivative of the bottom, when you have something that you've multiplied by and there's more than one part to it, you have to have parentheses around it. Otherwise, this looks like all this times 1 minus cosecant squared. Yeah, exactly, Gabrielle. We need the parentheses for sure. So when in doubt, err on the side of throwing in the parentheses around the, right? Basically, if this piece being the entire derivative of this piece means it kind of is one thing. It's a unit that has to kind of stay together. Yeah. All right. Let's kind of continue on. Yeah. So we'll talk about log. Let's see. Yeah. Oh yeah. Sorry. I was going to do some other. I guess we have to talk about logarithms first. So let's talk about the kind of big plan for today is to talk about how to differentiate things with different bases. So something like 2 to the x or 3 to the cosine of x. Also talk about how to differentiate logs with different bases. So the derivative, the natural log of x, the derivative of log base 2 of x. And then there's some other crazy stuff we'll talk about. But these are kind of the next thing. So we have to kind of address this first. So how do we differentiate the natural log of x? Well, it is possible to do it with the limit definition of the derivative. You could totally write, we're not going to do it, but I can show you the beginning of it. You can totally write this is the limit as h goes to 0 of the natural log of x plus h minus the natural log of x all over h. And then you can combine these together, and you can actually use that same kind of limit trick we used for e to the x if you want to. If you guys really want me to, I will do this, but I don't think it's super duper kind of, I don't know, I don't think it's really that educational. But again, if you want to see it, let me know, I'll totally do it. Instead, here's what we do. Say, okay, I know I'm going to start with y equals the natural log of x, because I'm going to use implicit differentiation. So then here's what I need. I'm pretending like we don't know how to take the derivative of natural log of x. So you need to rewrite this in a way where we can take the derivative of the things that we have. Well, I can rewrite this as e to the y equals e to the natural log of x. So e to the natural log of x is just x. So e to the y is equal to x. All right, let's differentiate both sides. What's the derivative of e to the stuff? Oh, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. What's the derivative of x? Well, that's just 1. Solve for y prime. Y prime is 1 over e to the y, but e to the y is equal to x. So y prime is 1 over x. There's your derivative of the natural log of x. So the derivative of the natural log of x is in fact 1 over x. And now we're going to do the same sort of thing, right? Derivative of the natural log of x is 1 over x. The derivative of, in fact, let me write it out. The derivative of the natural log of some stuff is 1 over your stuff times the derivative of your stuff. I almost always write it this way, but lots of people like to write it as one fraction where it's the derivative of your stuff divided by your stuff. This is actually worth making note of, because later on in this class, when we start talking about antiderivatives, we're going to often see a lot of things where you say, oh no, I want to know what function has a derivative, and the derivative ends up looking like, for example, if my derivative was 2x over 1 plus x squared, well, I could say, oh, the original function is probably the natural log of 1 plus x squared, because the derivative of this is 1 over the stuff times the derivative of the stuff. So if you can see that the top is the derivative of the bottom, you can be like, oh, the function we took the derivative of to get this was probably the natural log of the bottom. Kind of cool. It comes up a lot, actually. So then we can do all sorts of crazy things. Yeah, I can fix this. I don't remember that. And he's like, what's the derivative of the natural log of, I don't know, x to the 4th plus, I'm trying to throw in all the trig functions at some point, cosecant of 3x. Okay, well, let's see here. That's going to be 1 over my stuff times the derivative of the stuff. And the derivative of the stuff, let's say the derivative of x to the 4th is 4x cubed. The derivative of cosecant of x is negative cosecant of x times cotangent of x. So the derivative of cosecant of some stuff is going to be negative cosecant of your stuff times cotangent of your stuff times the derivative of that stuff. And yes, you could totally write all of this just on top of the fraction. It's just not the way I personally do it. I should, though, because it would totally save me board space, but I just don't. It's really because I like to think of it as the chain rule, right? I like to think, okay, the derivative of the natural log of some stuff is 1 over the stuff, and then we multiply by the derivative of that stuff. Let's look at another one. Let's say I want to do the derivative of the natural log of x to the 9th. Well, there's actually a couple things we could do. One option would be just to do it like normal. Say it's 1 over your stuff times the derivative of your stuff, which is going to be 9x to the 8th. But another way you could do this is you could use a rule of a logarithm, which is that the natural log of x to the 9th is the same as 9 times the natural log of x. Notice I've still written the derivative symbol because I still have to take the derivative. All I've done so far is simplify the expression, but I haven't actually differentiated. And then 9 times natural log of x, the derivative of a constant times a function, is the constant times the derivative, and the derivative of the natural log of x is 1 over x. Well, look, that's the same as what we got here. 9x to the 8th over x to the 9th, you can cancel 8 of those and 8 of those and get 9 over x. So, which way was easier? I don't know. They're both not terrible. But the point is that you can simplify a logarithmic expression into kind of easier logarithmic expressions to make it easier to differentiate. Let's look at another example. Let's say I wanted to take the derivative of the natural log of, I don't know, cosine of x over x to the 7th plus 2. I could totally do this the wrong way. It would still be right. It would just be the long way. You could do this as, all right, to be 1 over your stuff. This already seems terrible. Times the derivative of your stuff, which is going to have to use the quotient rule. So it's going to be bottom times the derivative of the top, which is negative sine of x, minus the top times the derivative of the bottom, which is 7x to the 6th. I didn't use parentheses there because each piece only had one kind of, there wasn't multiple things added or subtracted together. Divided by the denominator squared. Okay, that seems awful. It's right, but it's messy. Let me show you a better way. Trying to cycle through my black pens here so I don't use one of them all up. So that was kind of the long, terrible way. Here's the much, much nicer way. The derivative of the natural log of cosine of x divided by x to the 7th plus 2 is equal to the derivative of the natural log of cosine of x minus the natural log of x to the 7th plus 2. I'm just using, sorry, just one thing. I'm just using the rules of logarithms to break this up into many simpler logarithms. And now the derivative of the natural log of cosine of x is 1 over cosine of x times the derivative of cosine of x minus the derivative of the natural log of x to the 7th plus 2 is 1 over x to the 7th plus 2 times the derivative of x to the 7th plus 2, which is 7x to the 6th. If you wanted to make this a tiny bit simpler, you can write it as, let's see, negative sine over cosine is negative tangent of x minus 7x to the 6th over x to the 7th plus 2. Isn't that better? I think so. Right? It's certainly better than this hot trash mess over here. Which would you rather write? This one, for sure. This line here, the horizontal line. No, I did not. I was just separating my work. Yeah, that's just separate work. It's not one big giant fraction. No, it's not that weird. Okay. So I'm just doing it. I'm doing it different ways. Right? I took the derivative one time and did it this terrible gigantic fraction way, or we did it this way. We first broke up the natural log of cosine over x to the 7th plus 2 as the natural log of cosine minus the natural log of x to the 7th plus 2, and then differentiated each of those, which was simpler because they weren't terrible. I almost always, when I was a teacher of this class in a different university, I would almost always on an exam ask something pretty gnarly. Something like, for example, the derivative of the natural log of, I don't know, let's make it gross, x cubed times the square root of x squared plus 1 over, I don't know, 2 to the x times sine cubed of x. Terrible if you don't do the thing. So we're going to break this up. We're going to break it up into 4 different logarithms because I have x cubed, right? There's 4 different factors. There's x cubed, there's the square root of x squared plus 1, there's 2 to the x, and there's sine cubed of x. So we're going to break this up as the derivative of, I'm going to do it in 2 steps just to show you guys, but here's what you should know. The things on the top always get positive coefficients. The things on the bottom always get negative coefficients. So we can break this up as the natural log of x cubed times, I'm going to write this as x squared plus 1 to the 1/2 minus the natural log of 2 to the x times sine cubed x. And then we use the product rule for logarithms to break these up again. This is equal to the derivative of the natural log of x cubed plus the natural log of x squared plus 1 to the 1/2 minus, I'm going to show it this way, minus, okay, if I break this up using the product rule, it's the product rule for logarithms. It's the natural log of 2 to the x plus the natural log of sine cubed x. But this minus sign distributes. So we see that, oh yeah, both the pieces on the bottom will in fact have negative coefficients. And then one more simplification, which I do recommend you do all the simplification, bring down the powers. This 3 comes down, 3 natural log of x, plus this 1/2 comes down, 1/2 natural log of x squared plus 1. Minus this x comes down, x times natural log of 2. And this 3 also comes down because this is sine of x quantity cubed. So that's minus, right, we're distributing 3 natural log of sine of x. I do want to mention this power here does not come down, right? It has to be the power on the entire thing that you're taking the logarithm of. So if you've got a logarithm of some stuff all to a power, that power can come down. But if it's a logarithm of something to a power plus some other thing, then no, you can't do it, right? It's got to be everything raised to that power. And now we're finally ready to actually differentiate, right? All I've done so far is just use algebra to simplify this. Now we're going to differentiate, and we're going to get 3 times, well, the derivative of the natural log of x is 1 over x, plus 1/2 times the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of the stuff, which is 2x. Look at me writing it on top, like person trying to save space. Minus the derivative of x times natural log of 2. Be careful here. The derivative of natural log of 2 is not 1 over 2. The derivative of natural log of 2 is 0. So really the way you should view this is it's x times a constant. The derivative of x times a constant is just the constant, right? Just in case you guys are like, James, I don't know about that. Let me ask you a different question. What's the derivative of 6x? You all know this. You can type it in the chat if you wanted to. You could say it. You could show me some fingers. You'd be like, hey, James, that answer is 6, right? The derivative of a number, a constant, times x is just that constant. Same deal here. This is natural log of 2 times x. The derivative is natural log of 2. And then here we get minus 3 times the derivative of natural log of sine of x is 1 over sine of x times cosine of x. Yes, you could rewrite this as cotangent of x, but I'm not going to rewrite the whole thing, just to rewrite that one part. So that's how you take the derivative of something like this. You definitely want to do it this way, because doing it the long way, right, you would have to write 1 over all of this, and then you would take the derivative of all of this, and you have to use the quotient rule and both the product rule for the top derivative and the bottom derivative and the chain rule for some of the derivatives, right? It's just a gigantic mess. So don't do it that way. Or don't do it the way I didn't do it, right? Yeah. Okay, let's look at another, yeah, sure. Let's do another, let's go back and do an implicit one just for fun. Just for fun, right? So let's say I want to find the derivative of, yeah, let's So find dy dx for x cubed plus y squared plus the natural log of xy equal to 7. All right, same process. Yeah, no, I could definitely talk about that again. Yeah. So the reason the whole kind of the thing you want to stress here is that natural log of 2 is just a number. It's like 6. It's actually like 0.69, but it is specifically a constant value, right? Natural log of 2 isn't changing. And when you're talking about taking the derivative of something, you're asking about its rate of change. Let me erase some of this here. Let me put it this way. So I hope everyone is cool with this, right? That, oh yeah, we know the derivative of 6x equal to 6. You could, if you wanted to, use the product rule there. So what I'm actually doing there is I'm using the constant multiple rule. I'm saying, okay, the derivative of 6x is 6 times the derivative of x. Right? That's the constant multiple rule, where if you have the derivative of a constant times a function, it is literally equal to the constant times the derivative of the function. And it works whether your function is x or something more complicated, right? If I take the derivative of, 8x cubed, we know the answer is 24x squared. But the work that we're doing that we're not showing is saying, okay, it's 8 times the derivative of x cubed, which is 8 times 3x squared, which is 24x squared. But we're not actually showing that work because we don't need to. And no one wants you to, right? Okay. Well, it works the same whether your constant is nice, like 8 or 6, or whether your constant ugly, like natural log of 2. Right? If I take the derivative of, say, x to the 5th times the natural log of 2, well, again, that's just a constant. And so I can be like, well, that's going to be the natural log of 2 times the derivative of x to the 5th, which is going to be natural log of 2 times 5x to the 4th. Sorry for having to do there. I know it's not pretty, but it is what it is. The other way you could look at this if you wanted to, actually there's a couple ways you could look at this. So one way to approach this as well is say if I want to find the derivative specifically of x times the natural log of 2, I could use the product rule. Yeah. Order of multiplication is completely interchangeable. So the question being asked is, can we think of it as natural log of 2 times x? And yes, of course. Whenever you have things multiplied together, it's perfectly fine to write them in the other order of multiplication. The reason we write it like this usually is because if you write it the other way, people often make the mistake of thinking you mean the natural log of 2x, which we don't. We don't mean that. We mean the natural log of 2 times x. So that's why we usually don't write it this way, because it's a little less clear what we mean, or we have to be a little bit more careful about what we mean. But it is perfectly correct to say this and this are the same. So if you want to think of it that way, and that works for you, do it that way. The other thing you could do is you could say, I'm going to use the product rule. Let's do it from here. So using the product rule, it's the derivative of x, which is 1, times the derivative of natural log of 2, which is natural log of 2, plus x times, what's the derivative of the natural log of 2, everybody? Yes, 0. If you really wanted to be like super extra about it, you could say, well, James, the derivative of the natural log of stuff is 1 over the stuff times the derivative of stuff. And be like, okay, that's cool. The derivative of the natural log of 2 is 1 over the stuff times the derivative of the stuff, which is 0. Here's what you should really get through your head. I know natural log of 2 looks like a function. Or similarly, e cubed looks like a function. It isn't. It's a constant. If you don't see If you're finding d dx, the derivative with respect to x, which is usually the variable we're differentiating with respect to, if you don't see that variable in the thing you're differentiating, the thing you're differentiating is a constant, and its derivative has to be 0. Okay. Okay, I think I've done it to death. All right. But I'm definitely, yeah, no, totally, yeah. I'm happy to talk. You guys, I'm happy to answer your questions. Ask away. I'm very, very, very happy to just be like, you guys have questions about this? We will talk about it until you don't want to hear about it anymore. So back to this problem. We're finding dy dx for this expression. We can't solve for y, right? Often we would be like, I'm just going to solve for y and differentiate. We cannot do that. And that's usually the case when it's all jumbled up like this. So we're going to use implicit. Derivative of x cubed is 3x squared. The derivative of some stuff squared, because remember, we're thinking of y as a function of x. The derivative of some stuff squared is 2 times your stuff to the first power times the derivative of your stuff. I don't want to write the first power though, right? Using the power rule. And then the derivative of the natural log of x. Okay, so we know that the derivative of the natural log is some stuff. So I kind of, when I'm reading a function, I'm just looking for the outermost part, and I'm literally ignoring what's on the inside. I'm like, okay, I got the derivative of the natural log of whatever. The derivative of the natural log of whatever is 1 over the stuff times the derivative of the stuff. So that's going to be 1 over the stuff times, okay, now I have to actually think about what's inside there. The derivative of x times y, I have to use the product rule. The derivative of x times y is the derivative of x times y plus the x times the derivative of y. The derivative of y is the derivative of y. Y prime. Equal to, be careful, I see so many people accidentally write the wrong thing here. It's not equal to 7. It's equal to the derivative of 7, which is 0. Whenever you're using implicit, you're differentiating both sides of the equation. I will flippantly say the rest is just algebra. I know it's not that easy, but the rest is just algebra. Oh, I need to actually, let me think about one thing here. Is that something we can do? Oh, I did. So, you know what? I didn't follow my own advice. So I'll point out that, so I'm going to show you guys something that I should have done something different, which is fine. If you distribute this, 1 over xy times y is going to be 1 over x. And 1 over xy times xy, the x's will cancel and you get y prime over y. Or 1 over y prime. But if I had been a little bit more observant, I would have made the choice and said, oh, look, I could write this as x cubed plus y squared plus the natural log of x plus the natural log of y equal to 7. That might have been a smarter way to do it, so I didn't have to use the product rule. And then I could have differentiated both sides and said 3x squared plus 2 times my stuff times the derivative of my stuff plus the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over y times y prime. That might have been better. I think that probably would have been better. So definitely when you see natural log of a product or a quotient, it's usually in your interest to simplify that before you differentiate. Okay. Either way, we're trying to solve for y prime. So let's isolate the y primes. So we're going to keep those on the left side, bring everything else to the right. I'm going to go ahead and erase this here since it's literally the same as that. So I've got 2y prime plus 1 over y prime equal to negative 3x squared minus 1 over x. Factor out of y prime. Y prime times 2y plus 1 over y equals negative 3x squared minus 1 over x. And then divide both sides by 2y plus 1 over y. This is equal to, so this gives me y prime is equal to negative 3x squared minus 1 over x over 2y plus 1 over y. Yeah, that's probably a little bit better way to do it, is to first simplify this logarithm into smaller, simpler logarithms. I should say we expand the logarithm into smaller, simpler logarithms. Right. Yeah. So let's talk about different bases, because they do come up. So here's what I'll say in general. The nice thing is the rules are pretty much essentially the same as they were before. Meaning, if you know how to differentiate e to the x and the natural log of x, then you will quickly learn how to differentiate different base to the x or log with a different base of x. So let's try and differentiate 2 to the x. Okay, well, here's the deal. Oh, so there are two. So I've always done this one way. I'm going to show you the way I do it, but I'll also show you the way that your teacher might show you how to do it. So I'll show you both ways. I think one way, so really, sorry, I'm saying a lot of words about something. Really what I think about this is you should just memorize how to do it, right? There's a very, very straightforward pattern that you'll see after you do it a couple times. So here's what we get. I'm going to write y equals 2 to the x. I'm going to take the natural log of both sides. The natural log of y equals the natural log of 2 to the x. I'm going to bring the x down. So the natural log of y equals x times the natural log of 2. And now it's really great that we have the big conversation about how to differentiate x times the natural log of 2. So differentiating both sides, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Again, stop me if you have questions or write something in the chat. Like, James, I don't really get what you're saying there. Please let me know. But I think we're all hopefully very comfortable now with the fact that the derivative of x times a constant is just 1 times the constant. Now we're going to solve for y prime. So y prime equals y times the natural log of 2, right? Just multiply both sides by y. And then finally, remembering that y is equal to 2 to the x, we get that y prime is y times the natural log of 2. And what's kind of great about it, I don't know if great's the right word, what's nice about this is it doesn't matter what base we use, right? If we had used 5, just replace the 2 with the 5. The derivative of 5 to the x is, well, y equals 5 to the x, natural log of y, natural log of 5 to the x, natural log of y equals x times natural log of 5. 1 over y prime is 1 times natural log of 5. Y prime equals y times natural log of 5. Y prime equals 5 to the x times natural log of 5. So basically, more generally, if you want to find the derivative of any base to the x power, it's equal to that same expression. And again, remember I said this before, if you differentiate an exponential thing, that exponential thing always pops back up. But then if your base is different than e, you have to multiply by the natural log of that base. In fact, it's also true if your base is e. The derivative of e to the x is e to the x times the natural log of e. It's just the natural log of e is equal to 1. So that's kind of great. And I really don't think you should derive this really ever, but it is good to see how to get there. You should really just remember, if you're taking the derivative of like 4 to the x, the derivative of 4 to the x is 4 to the x times the natural log of 4. Now, yeah, there is another way of doing this, and I should show it to you because I wouldn't be surprised if your teacher showed it to you this way. I had definitely not seen this other way of doing it until maybe a year or two. I was like, oh yeah, I guess that works. It's just not what I ever would have thought of. So you can also find the derivative of, let's do a different one. Let's say 6 to the x. We know the answer already. We know the answer is going to be 6 to the x times the natural log of 6. But let's talk about a different way to get there. You can rewrite this as the derivative of e to the natural log of 6 to the x. And then you can use the logarithm rule to say, okay, that's the derivative of e to the, bring that x down in front of the logarithm. So it's e to the x times natural log of 6. Okay, now we're going to differentiate. And we know that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So that's going to be e to the stuff times the derivative of the stuff. I'm just going to write literally as the derivative of x times natural log of 6. But we've seen it a few times now. The derivative of x times a constant is just that constant, right? Natural log of 6 is some constant. I don't know what it is, but it's a constant. So that's going to be e to the x times natural log of 6 times the natural log of 6. But wait, e to the x times natural log of 6 is the same as e to the natural log of 6 to the x, which is the same as just 6 to the x. This is 6 to the x. So then, oh yeah, this is in fact equal to 6 to the x times the natural log of 6. I will say, if you remember, I will say you should just memorize it, right? This rule is one that can be memorized relatively easily. But if you actually have to do it, and like your teacher says, I want you to show the work for this, and you can't just, you're not allowed to just like say, like, I know the derivative already is 6 to the x and natural log of 6. This is probably the easier way to show the work, right? You don't have to, you also, like, if you're doing it this other way, where you're trying to take the derivative of 2 to the x, you have to remember, oh, I need to say that y equals 2 to the x, and then take the natural log of both sides, and then use it as differentiation. Whereas this way, all you have to remember is that you can rewrite 6 to the x as e to the natural log of 6 to the x. Okay, so someone asked how I knew that e to the x natural log of 6 was in fact equal to 6 to the x. And really what I was doing is I was just kind of undoing the work I already did, right? I started with what I really did, so I wanted to take the derivative of 6 to the x. So the work we started with was we said, well, I'm going to rewrite 6 to the x in a way that I can take its derivative. So we said 6 to the x is equal to e to the natural log of 6 to the x. And then we brought the x down in front of the natural log. So you get e to the x times natural log of 6. So then we took the derivative of that, and we got e to the x times natural log of 6 times, the derivative of the exponent. We simplified, we took the derivative of that, which was just natural log of 6. So then we got e to the natural log of 6, sorry, e to the x times natural log of 6 times natural log of 6. But then, hey, look, that is just that, which is just that. So that's what we're doing there. We're just working kind of backwards. This is one of the reasons I don't prefer this method, is because you have to kind of do this kind of thinking backwards. But it's really just, oh yeah, we said this thing was that thing, we're just saying it's that thing again. All right, so let's see, yeah. Let's go ahead and do this. I think this is a good way of doing it. So the rule of thumb that I always like to encourage you guys to remember is that if you are differentiating an exponential thing with a different base, you always have to multiply by the natural log of that base. And it's true whether it's something easy like 3 to the x, or something a little more challenging like 3 to the x squared. Let's say I want to take the derivative of y equals 3 to the x squared. And there's so many different ways you can do it. I'm more of a fan of taking the log of those sides, the natural log. So the natural log of y equals the natural log of 3 to the x squared. Bring the x squared down in front. The natural log of y equals x squared times the natural log of 3. Differentiate both sides. 1 over y prime. So I should point out, often this method of logarithmic differentiation, where you take the natural log of both sides, comes up a lot. And when you use it, you're almost always taking the derivative of natural log of y, and it's always going to be 1 over your stuff times the derivative of your stuff. So you should definitely get comfortable with saying, oh yeah, the derivative of the natural log of y is 1 over y times y prime. Derivative of the right-hand side. So again, look, I have a function times a constant multiple. Derivative of something times a constant is the derivative of the something times the constant. You can write it in front if you want, right? You can say, oh, James, you mean you're taking the derivative of natural log of 3 times x squared? Yes, I do. And the derivative of a constant times x squared is the constant times 2x. It's perfectly fine to write it that way. I just don't. And then we solve for y prime. So y prime is equal to y times 2x times the natural log of 3. So my y prime here, remembering that y is 3 to the x squared, is 3 to the x squared. Now I made a little mistake there. I accidentally wrote 2 to the x. It should be 2x. Don't make that mistake. It's easy to make. So my derivative is 3 to the x squared, which is my y, times 2x times the natural log of 3. And yeah, I should do one more. Let's do one more. Let's say I want to take the derivative of y equal to 5 to the sine x. Well, again, I'm going to use the same process. I'm going to take the natural log of both sides. I'm going to do it the other way just to kind of show you both ways. So I'm going to do the e to the natural log thing. So I'm going to take the derivative of, so it's the derivative of e to the natural log of 5 to the sine x. I don't love doing it this way, but again, I think your teachers might want you to do it this way. So I'm showing you both methods. Really, we're going to get to the shortcut in like a minute. So e to the natural log of 5 to a power, this power gets to go sit in front of the natural log. So that's the same as the derivative of e to the sine of x times the natural log of 5. We know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, but the derivative of that stuff, the derivative of sine of x times the natural log of 5, that's a constant. So the derivative of this function times this constant is the derivative of sine, which is cosine of x times that constant. What I often say is constant multiples get to hang out, right? Not constants, right? The derivative of a constant on its own is 0, but a constant multiple where it's multiplied by a function of x, it hangs out, it sticks around, it's attached to that function of x. So sure, the function might change, but the constant's its friend, it's sticking with it no matter how it changes. It's a very good analogy, not really. And then, so I'm going to do the same thing I did before. So the person who asked how do we get from e to the x times natural log of 6 back to the 6 to the x, same thing here, right? We use the fact that 5 to the sine of x is equal to this, is equal to this. So I know that this part here is the same as that. So I'm going to rewrite this because it's more standard to write it this way as 5 to the sine of x times cosine of x times the natural log of 5. So here's what I want you to observe. Would we not make the left side of the equation d dx e to the y? No, because I'm not taking the derivative of e to the y. I'm taking the derivative of e to the natural log of y, which is just y itself. Yeah. Right, so that's actually, it's a good question. The difference between these two methods is that this method, you have to take the natural log of both sides and differentiate both sides and use implicit. This method, you just get to manipulate what y is equal to and take its derivative in a more kind of straightforward way, whereas implicit's kind of around. Either way is correct. My preference is this, but whatever you do, I don't care, right? As long as it works for you and works, then it works. But here's what I want you to see about both of these. The derivative of some base to some function of x is that same expression times the derivative of the stuff times the natural log of the base. The derivative of 5 to the sine of x is 5 to the sine of x times the derivative of sine of x times the natural log of the base. And so let me write down some rules for you. So typically, And again, I can't speak for your professor for sure, but typically it is perfectly fine for students to just memorize these things and not have to like justify them. And so let me kind of actually start back a little bit. So we know that the derivative of e to the x is e to the x. And we just learned that the derivative of some other base, like a to the x, is a to the x times the natural log of a. Now you might notice this rule actually encompasses that rule. Well, so someone asked, so the derivative of e to the natural log of y, well, it's not, yeah, it is equal to y prime because e to the natural log of y is just y. So yes, of course, that would be the derivative of y. All right, remember, e to the natural log of a thing is just the thing. Okay, and now we also have the chain rule versions of this, right? The derivative of e to the, I'm going to write, there's so many ways you can write it. I really like to write stuff, but I'll use the slightly more standard notation. The derivative of e to the u of x, or u is a function of x, is e to the stuff times the derivative of the stuff. Well, the same thing is true for a different base, just that you have to also account for the natural log of that base. So the derivative of a to some function of x, or a to the u of x, is a to the stuff times the derivative of the stuff times the natural log of the base. So the only difference in differentiating e to a thing versus 2 to a thing, or 5 to a thing, or some other different base is that, well, first of all, you do have that base. And second of all, we have to multiply by the natural log of that base. Kind of great. So if someone asked me, for example, James, what's the derivative of 4 to the secant of 3x? Well, I say, okay, I know the derivative of 4 to the stuff is 4 to the stuff times the derivative of the stuff times the natural log of 4. So it's 4 to the stuff times the derivative of that stuff. Okay, the derivative of secant of 3x is secant of your thing times tangent of your thing times the derivative of your thing. And then we also have to multiply by the natural log of our base. It's not terrible once you recognize that all these patterns are really the same pattern. Really, all of these rules are encompassed in this one last rule. So if you had to remember just one of them, that's the one to remember. Right? Because if your base is e, then natural log of e is just 1, and that goes away. And if your exponent is just x, then you get a to the x times the derivative of x is just 1 times natural log of a. So this rule will get you all those rules. All right, yeah, we have enough time. Let's talk about different bases for logarithms. We're not going to quite get to, yeah, we can do that, sure. Yeah, we're not going to quite, so next week we'll get to really super fun things like the derivative of x to the x, where your base and your exponent both have variables, but I don't think we're going to have quite enough time today, which is fine. So let's say I want to take the derivative of y equal to log base 4 of, sorry, what have I got here? X to the 7 plus 3x squared. There's actually 2 very valid ways of doing this. The easiest way is actually to use the change of base formula. So I don't know if you guys know the change, I don't remember if I talked about it last class or not, but the change of base formula says that if you got, say, log base a of x, you can write that as log base b of x over log base b of a, where you can pick b to be any base you want. So of course the base we're going to pick is base e, the natural base. So we could totally write this as natural log of x to the 7 plus 3x squared over the natural log of 4. But dividing by the natural log of 4 is just multiplying by the constant 1 over the natural log of 4 times the natural log of x to the 7th plus 3x squared. Constant multiples just hang out, right? That's a constant multiple times a function of x. So when you take the derivative, you're going to get that constant multiple hanging out times the derivative of the natural log of some stuff, which is 1 over your stuff times the derivative of that stuff, which is 7x to the 6th plus 6x. Totally not terrible. Let's look at a different way of doing it, because there is another way. Yeah. Let's say I want to take the derivative of, what have we got here? Y equal to log base 2 of e to the 5x plus sine of x. Okay, so instead this time I'm actually going to rewrite it. I'm going to write, we know how to change a logarithmic equation to an exponential equation. If y equals log base 2 of some stuff, that means 2 to the y power equals the stuff. Let's differentiate both sides using implicit differentiation. We know the derivative of, see, this seems like a harder way to do it, I gotta say, but it'll still produce the same result. The derivative of 2 to the y, well, derivative of 2 to the stuff is 2 to the stuff times the derivative of the stuff times the natural log of your base, which is 2. The derivative of this stuff is, let's see, e to the 5x is e to the 5x times 5. Derivative of sine of x is cosine of x. Solving for y prime equals, I'm going to write this as 5e to the 5x plus cosine x divided by, not all that, sorry, divided by that. Divided by 2 to the y times natural log of 2. Okay, but now here's where we do that tricky thing again. We're like, hey, wait, we know what 2 to the y is. 2 to the y is e to the 5x plus sine of x. So look, we exactly get 5e to the 5x plus cosine x over e to the 5x plus sine of x times the natural log of 2. Or here's how I would say it. The derivative of log base 2 of some stuff is 1 over the stuff times the derivative of the stuff divided by the natural log of the base. The derivative of log base 4 of some stuff is 1 over the stuff times the derivative of the stuff divided by the natural log of the base. And more generally, the derivative of log base a of some function of x is 1 over the function of x times the derivative of the function of x times 1 over the natural log of the base, or dividing by the natural log of the base. So yeah, I got time. So let me sum up the logarithmic derivative rules for you guys super duper quick. Like, we know that the derivative of the natural log of x is 1 over x. And I guess we didn't actually talk about it specifically, but I will tell you the derivative of log base a of x is going to be 1 over x natural log of a. So right, it's 1 over x, and then we also have to divide by the natural log of the base. So no, let me say the next bit too. And then we know more generally the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then we just said, but I'll say it again, the derivative of log base a of some stuff is 1 over the stuff times the derivative of the stuff times 1 over the natural log of the base. which people probably usually write as u prime of x over u of x times the natural log of a. People often write this as u prime of x over u of x. Okay, so here's kind of the takeaway. For exponential functions, I know I erased. For exponential functions, like, derivative e to the x versus the derivative of a to the x. Sorry, that looks terrible. When you differentiate an exponential function with a different base, you multiply by the natural log of that base. When you take the derivative of a logarithmic function with a different base, you divide by the natural log of that base. Yes, when you're taking the derivative of a log with a different base, your answer is going to have the natural log of that base, which is just log base e. So I know it's 10:20, but let me do one more, just so I can kind of give you guys the sum up here. If someone said, hey, James, I would like you to find the derivative of, I don't know, the derivative of log base 6 of, what have I got here? Oh, that's too easy. Let's say it's something like x to the 4th plus 5 to the x. Yeah, let's make it saucy. Then I would say, okay, I know how to take the derivative of log base 6 of a thing. It's 1 over the thing times the derivative of the thing. And I need a little bit more space for. And then I also need to divide by the natural log of the base. The derivative of this is 4x cubed plus the derivative of 5 to the x, which is 5 to the x times the natural log of 5. And then again, you could write this more compactly. I like to write it out this way because it really kind of keeps the parts separate for me. I'm always doing 1 over the stuff, derivative of the stuff, and then divide by the natural log of the base. But if you prefer, and you might prefer, you could definitely compactify this as 4x cubed plus 5 to the x times the natural log of 5 over x to the 4th plus 5 to the x times natural log of 6. But I really personally encourage you to think of it this way first before kind of trying to compress it down into a smaller expression.